Okay, so let's talk about first topic over here, difference between FPGAs and ASICs. So we know that FPGA stands for Field Programmable Gate Array, something that can be programmed on the fly. And ASICs are something which is application specific integrated circuit, which is designed for a specific functionality. So if you aren't aware of these two flows, the whole design flows, we have got a couple of uploaded free videos on Semionics Academy. You can have a look at the sessions on analog flow and digital flow and the FPGA flow. In this, you can easily correlate and figure out that yes, there is decent amount of difference when it comes to the flow as well as the time it takes to design an FPGA based design and an ASIC based design. So if you can see over here on this picture over here, you have got this five uh, topics over here wherein the reason it says like why we go for FPGAs, the reason is volume, efficiency, customization, time to market, and all of this. Let's take one by one about this. Okay, flexibility or and customization of integration. We know that FPGA will be an easier choice for you to design it more quickly and to be able to meet the time to market. Okay, so in short, if I have to tell you uh, what it works is, let me get back to that out here. Okay, let me get back to the screen. Okay. So FPGAs generally, if you have seen the flow, you write the code, a synthesizable code, and you burn it on an FPGA, right? Whereas in ASIC, you have to, uh, you know, uh, build a whole design. It takes easily around 6 to 8 months for you to build a proper ASIC product, right? Whereas over here, say today, for example, you have designed something which is of 64-bit. It's working fine. And the customer comes and says, yes, the product looks okay. Can you enhance this for a 128-bit? Okay. Using the same functionality, and they may come up and say, okay, can you add these 3 or 4 more pins to this? So since it's easier to edit the code. So what we do is you just write a synthesizable code, increase the bit factor from 64 to whatever 128, and then again you can add more pins. You run it down the whole FPGA flow, and you reprogram the whole FPGA, and your FPGA with the latest update is ready. Whereas if you have to do the same thing for an ASIC, it would take decent amount of time. If you understand both the flows, then you would realize that how different it is to design this. Okay. But there are pros and cons of going for, uh, you know, the kind of things as well. Okay, let's get back to the screen here. Okay, so now but if you see a button, I see tailored to a specific task. If you want to design something very, very specific, right, for a particular application, then ASICs is the way to go. Performance and efficiency, right? ASICs are more efficient comparatively. Yes, because they are designed very precisely. You can use lots of low power design techniques. You can play around with hell lot of a design related things in an ASIC to make it more portable and power efficient. Whereas FPGA say, even though you create an FPGA, you have to use it on a board. Right? You need other supporting documents, other supporting device or circuitry for it to function. Okay, whereas ASIC is designed specific for a particular task. So that's why it is in fact designed for a lot more power efficient in a more power efficient way. So budget and time to market. FPGAs are quicker to design, but in the long run, right, it is more cost effective. What it's trying to tell you over here is, yes, even though FPGAs might be quicker to design and it might not cost you that much, right, comparatively, right? So you've got a board over here, you need a FPGA, and along with that, you will have a processor outside, you will have other peripherals. This is the PCB board, okay? Your FPGA sits on that, okay? So So it's more cost effective to design this and more time consuming. But when it comes to an ASIC, right, the initial cost of making an ASIC, okay, is much higher than compared to an FPGA. We call it as the NRE cost, non-recurring engineering cost. So, but since the ASICs are so tiny, right, it goes in terms of nanometers and all of that. So the overall, the number of dies what you can produce, chips what you can produce on a whole die will be in thousands, right? So all in all, if you see when it comes to bulk production, the cost of each die becomes much smaller. So thereby, so you got to decide what you want to go for. What is the application? Based on that, you take a call whether to go for an ASIC or an FPGA, right? That's where the difference comes in. Obviously, I've spoken about the power consumption part of it. Okay, so these are some of the tiny factors or tiny few. I've mentioned very few differences over here. So that our main topic here is about design porting, but then some differences will give you a slight amount of idea of why are we going for ASICs. Now, if I'm talking about ASICs, let's move to the next slide and see that if ASICs are that better compared to FPGAs, then what is the need to go for FPGAs? Why are we going for FPGAs, first of all, if that's the case? But to answer that, you need to know when to choose an FPGA. Okay, you need to be able to decide for what application FPGAs are suitable, what kind of applications ASICs are suitable, right? Now, if you are having a product over here which needs programming from time to time, okay, based on, you need to make it more flexible, right? If that kind of design is there, that kind of requirement is there, then FPGAs are certainly the best choice to go for. Okay? And another thing here is there's something called as ASIC prototyping. Means, right, that this is the design. We are just talking about the digital design over here. We have got analog mixed signal designs as well, right? But for ASIC prototyping over here, right, if at all you're not sure whether this will work or no, right? If at all you want to check a design, how efficient it is, right? You just try to make a design on an FPGA and run it on an FPGA and see how well it works. But before you go for an ASIC, you make a prototype of that on an FPGA and see how well it works. If you come to a conclusion that yes, this is working fine for me, and when you miniaturize this to an ASIC, yes, this is going to be a lot more better product. So you're trying to do a kind of testing. You're doing a ASIC prototype and then trying to see that whether the functionality, whether what you want is, realizable or no. Once you're sure that it's working fine over here, then you go for a same thing, whatever you have done prototype, but make it more specific on an ASIC and do the bulk production later. Now, as I mentioned, market needs a ready-made solution, right? So you don't have to go every time back to the design house and and tell that okay, you make this chip for me. They want ready-made solution, instant solutions, right? Wherein you want to program things on the fly. The edits should happen within a span of few days. Whereas in case of ASICs, yes, it is very well possible, but it takes time, right? So that's where the question comes, that's where FPGAs get the brownie points. That's where you decide that okay, in certain cases, yes, FPGAs are more efficient and more suitable over there, whereas ASICs might not be the choice for that. Okay. Now the other thing here is we've got something called as reprogrammable SoC level embedded system design. Let me just briefly tell you what I'm talking about over here. Okay. So now we know that your PCB has got the FPGA over here. There are other peripherals. There's a processor over here. There's a memory unit over here. There are resistors. There are capacitors. Blah blah. All of it, right? And all of this are connected together. There's a PLL. There's oscillator. Blah blah. All of that. This is whole of it is a PCB. Now, as we know that the technology advanced, you are trying to put all of this logic within than FPGA. Right? You're programming everything. You're putting the the IOs, the logic, the custom logic, what you want to put, all the other peripherals is miniaturized and put it on an FPGA. Now you have all of this processes and everything, but everything can't be put on an FPGA, right? So, but as the technology advanced, we can call it as SoC. What is SoC? SoC is a processor along with its peripherals, right? It's called as a SoC. This you have got processors, FPGA, everything. This is a embed. Generally, we call it as an embedded system design. Now, if you're having all of this on a single SoC, it's called as SoC level embedded system design. Okay, so you have got a FPGA over here. You have got a soft core processor. Let's say, for example, a Neos 2 or a Leon. These are soft core processors. When I say soft core, what it means is anything, whatever is there on this FPGA is programmable. It's obvious. So rather than having an FPGA outside on the PCB board, when you can have a programmable processor on the fly, it makes it a lot easier to program the processor itself. At any point of time, a customer tells you, okay, give me a 64-bit design. Okay, fine, tuck, you change the design and you hand over it. You want 128? Yes, for the same functionality, right? With a little bit of edits, it's a lot easier. So processor, like probably you will have a FPU over here, and then you will have GPIOs, you will have lots of a memory, FIFOs, RAMs, and all of that. This DMU, all of this on a single FPGA, which means what? All of this is a software code. I mean to say a Verilog or a VHDL code. Okay, so that's where on a single FPGA. Earlier you had a FPGA with peripherals on the PCB. Now you have got all of these things. Yes, certainly we do need a PCB, right, to place the FPGA and make it work. But lots of components which were there earlier on an FPGA on the PCB board are now inside the FPGA itself. So all of this is soft core. When I say soft core, it is programmable using VHDL or Verilog. So that's why it is called as SoC level embedded system design. Now, if you want to design something like this, yes, FPGA is a choice. But still, the analog components, the analog designs, the sensors, the temperature sensors, the PLLs, the whatever the analog components are there to design, right? Everything cannot be accommodated on an FPGA. Yes, earlier one of the FPGA vendors did come across FPGAs with analog components called Igloo. I think Igloo was the name of the FPGA over there from Lattice Semiconductor. So, but over here, all in all, if you want a lot of analog and mixed signal design, yes, you got to go for ASICs. But yes, even this is a decent amount of, a hell lot of improvement rather than having such a huge PCB board, you can have such a small FPGA PCB board and your FPGA is containing everything, whatever was there here with little bit of analog components, power up, button switches and all. So that's where the difference comes. And if you want to design something like that, that's where the SoC level embedded system design comes in. And that's where FPGA shows a lot of, demand or ask for these things. Okay. So here you can see if you want to decide anything specific, you go for ASICs. If you want to design something more generic, more programmable, that's where you go for an FPGA. So that answers the question, when would you choose an FPGA? Now, the other thing is, what is the need to port here? I mean, obviously, certain portion of the explanation gives you an answer that what's the need, it's already answered. But when you need more dense logic, right? Because your FPGAs, obviously, there is a limited programmable logic unit over there. So if you want to have an ASIC, you can easily target to a lower technology node and get the job done. Okay, so there is a lot of difference between technology to technology when you're designing an ASIC. You can have millions and millions and millions of transistors and logic, within a single ASIC. Okay. Now, better performance for a lesser per unit cost. I'm not talking about single unit. Single unit, yes, on the first run when you want to make an ASIC, yes, it is expensive. But when you design it in bulk for, it's not just one place where you're selling your chip in all the electronic products all across the globe. So the per unit cost becomes much cheaper over there. But and also you're getting a power efficient uh, product, a better product comparatively. Yes. So that's what it is. And the other most important advantage is since ASICs are very tiny, compared to FPGAs, right? But they're suitable for lots of IoTs, handheld devices, battery operated devices, right? So all in all, it is if you compare based on the application, one needs to decide whether to go for an ASIC, whether to go for an FPGA. If we just talk about FPGA and ASIC, yes, there are plus points, more plus points on the ASIC, less plus points on an FPGA, but there are scenarios where an FPGA wins the case all in all. So it's just based on the application over here. So that's about the difference between an FPGA and ASIC over here. Now the thing is, in the next slide, we will next video, we will try to understand the other aspects of porting. We'll get a little more deeper into ASIC porting. Here I have given you an idea why are we going for FPGAs. Here, if you see here, there's so many FPGAs that can be built into a single ASIC. Right. In the next session, we will talk about the ASICs and what is the importance of that, how to tackle all these situations. You can consider that FPGAs over here, are a decent choice, but ASICs are a lot better comparatively when it comes to design porting. So let's watch the next session.